down the question. We want to know how fast the area was growing when? When the radius is 4 feet. So when this radius is 4 feet, that's the instant I'm talking about. At that instant, how fast was the area growing, right? So my general picture, everything's moving, and then I take a picture right here at that moment. I want to know how fast the area was growing. All right, what are we given? Okay, I'm going to write down over here, 0.5 feet per second. Hey, feet per second. Feet per second is a speed, right? Feet per second is a speed, and a speed is a derivative, right? This is the derivative of what, though? This is the speed of what? The radius. How do you know? It says it right there, right? The radius is growing. So isn't this the change in radius with respect to time, right? Seconds. So couldn't I write that I'm given the rate of change, dr, the rate of change of r with respect to t is 0.5 feet per second. It's critical that you understand that the given information is actually giving you a derivative. That is the rate of change of the radius with respect to time is given to you. Yeah, what are you trying to find? What do you want? The question says, find the rate at which the rate at which the area, right? It says that? The rate at which the area is growing or something like that. So you want... We will, but what do we want? Do we want to know the area? Let me bring the problem back up. What did it ask for? Well, what is it? Then how fast, right? Fast, we're talking about speed, right? I want to know how fast what's growing? The area, okay? So I want to know the speed of the area. The speed of the area means the derivative of the area, right? So I want dA dt, right? I want dA dt, right? I want to know how fast the area is changing with respect to time. But when? When do I actually want that? At 4 feet. At what's 4 feet? At the moment the radius is 4 feet. Okay, look at this. We've got everything we need. All right? I drew a picture of a circle that's growing. Okay? I drew the picture at the exact moment in time that we're talking about. I wrote down what I was given, which was a derivative, and I wrote down what I want, which is another derivative. And I also wrote down when I would like to know what this is. All right. I'm trying to find dA dt. That means I now need to have some equation that would have a in it, right? Yeah. Because if I differentiate that with respect to time, won't I get a dA dt? So I now need to come up with an equation. Any equation I can think of that has a in it, the area of a circle, and it would be really nice if that equation also had r in it, because if I differentiate it, I'll get a dr dt, won't I? So is there some equation, right, that I can think of that connects the area of a circle to its radius? Well, of course, right? Area is pi r squared, right? So every problem is going to be different. When we do these, every one of these problems is different because you're going to have different variables here, and the equation that you use to connect these is going to be based on your knowledge of the geometry of the problem. All right, so I'm going to write down the equation. Now, I'm going to have to scroll down. On this page here, see I scroll down here and it says equation. It has a space for the equation. I'm going to go ahead and just put the equation there. Is that all right? I'm going to leave the pic. No, I won't leave the picture. Okay, the equation I'm going to use is a equals pi r squared. Why am I using that? Because it has a in it. And I want to know something about how fast a is changing. Also, it has r in it. And I know how fast r is changing. All right. So I have a question before we do this. How fast am I running right now? I'm not running, right? Okay. So if I was running and now I said right there, when I snapped my fingers, how fast was I running? That would make sense to you, wouldn't it? But if I stop myself and say, how fast am I going, you're not going to be able to say anything, right? So you know how here we had r's 4? Do not plug 4 into this formula, because if you plug 4 into this formula, you have now stopped the circle from moving, right? And now this entire side would become a constant. And if you differentiate it, what would you get over here if that's a constant? You get 0, and then that would basically mean the question that you just answered. When I said, how fast am I running? You said, you're not. 0. That's because I was frozen. You have to do this thing where you're allowing things to move and still allow them to move to figure out that rate of change. And that means we have to differentiate before we fix the r, before we fix anything. So let's take the derivative of that. And what should we differentiate that with respect to? D over dt, which we just did, didn't we? Yeah. Okay, so, and what did we do? So look at your work from before. It was dA dt equals pi 2r dr dt. There we go. That was our implicit differentiation. And we said what this meant was that if we ever want to know how fast the area changes with respect to time, we're going to need to know two things, right? We're going to need to know the radius. Do we know the radius at the moment we're talking about? What is it? 4. Do we know the dr dt? Do we know how fast the radius is changing? Yes, it's 0.5, right? Just plug that in, and that's going to be your dA dt. So this is our scratch work section. So for scratch work, now I'm going to plug everything in. So dA dt will be equal to pi times 2 times 4 times, I'm going to put a half. Is that all right? Instead of 0.5? Notice I'm not putting any of my units on there. Some calculus professors are pretty adamant about putting units on here. I'll show you why I don't care about the units in a second. I mean, we're going to put units on our answer, but I'll show you why I'm not going to carry them through the whole problem, all right? All right, let's clean this up. That goes away, right? Our answer is 4 pi. Right, 4 pi. I'm just going to leave it at that. So dA dt is 4 pi, which is some number, I don't know, around 12 something or another, right? But it's a measurement of area, isn't it? Well, not area, area with respect to time. What are the units that I'm using in this problem? Feet, right? Feet. And how do you measure something when you have feet? How is area measured if you have feet? Feet squared, right? So what I'm going to have is in the numerator, I have square feet or feet squared per, now the denominator is time, and how is time measured in this problem? Seconds. So there you go. See, I don't even care about all the units in here because this tells me the units of my answer. It's the unit of the area, which is square feet, over the unit of time, which is seconds. So again, we've got a circle. It's growing, right? It's growing, it's growing, it's growing. It's constant. The radius is changing at a constant rate. And at the exact moment that the radius was 4, here's what I can tell you. The area at that instant was changing at exactly 4 pi square feet per second at that instant. It's important to know, though, that an instant later, it's different, right? An instant later, it's a different rate of change. All right. I know y'all want a break, and we can have a break in about 10 minutes. But let's see if you can do this one. That was our answer. 4 pi. You could do it as a decimal if you want, but that's the exact answer. Take a look at that one. What's different here?
It's a circle. Wait.
Yeah, this is a circle that's growing still, right?
Yeah.
But what's different is that instead of me saying that the radius is growing at a constant rate, what's growing at a constant rate? The area is growing at a constant rate. The area is growing at a constant rate. Let me show you the picture of this scenario, the animation of this scenario first. So the thing that's constant here is how fast the area is growing. Look at this number for area. See that number, how it's just counting? There's the same rate to that counting. But look at the radius, watch. In the beginning, it's fast, 2, 3, now it's slowing down. 4, right? It's almost like, imagine pouring like a can of oil onto the ground or something like that. And you've got this puddle that's growing, right? Initially, it goes fast, but as it grows, right, if you're pouring at the same rate, it's got more area to fill up, so it slows down how fast that's growing. See, that's different, right, than the last problem. In the beginning, it's coming, this radius moves fast, real fast, and then it starts to slow down. It's almost like instantaneous fast in the beginning, but it starts to slow down. All right, see if you can do it. Do you want me to put that sheet back up there or no? Yeah? I'll write it down on the side, the things that you should do here. Right, you want an instant picture. You want a general picture where things are in motion. You want to write down what you are given, what you want. Then you want some equation. You want to do your implicit. You want to do scratch work. And then you want your answer. And these 4 right here can be done in any order. It doesn't matter which of those you do first. And then we're going to take a break until 2:40. So see what you're going to do in the next 5 minutes with this, and then take a 5-minute break, and we'll come back and we'll do this problem together. I'm going to start working it out up here silently and see if y'all are getting the same thing. I went ahead and turned the 1/5 into a decimal. Actually, probably be fine to have it as a fraction.
Oh, yeah. All right, let's finish this up and then we'll take our break, okay? So I have a picture of a circle. At the instant in time, the only thing I'm given is that the area of it is 5 square feet. So I put that there, right? Then generally I just drew a circle. I threw a radius on there and I just said, hey, I just know that the area and radius are connected by this formula, just as like thinking about it, you know? Now I'm told how fast the area is changing with respect to time. How do I know that? If the area of the circle is increasing at a constant rate, rate is a derivative, so this is the derivative of the area with respect to time, is 1/5 square feet per second, that's given. Then how fast? Okay, I want to know the derivative, how fast, it's a speed, right? The speed of what? The radius. Okay, the speed of the radius with respect to time is what I want. At exactly the moment that the area is 5. Everyone understand all that written out? Once I'm here, I know that I need to come up with an equation that connects A and R together. So same formula we've been using, A equals pi r squared. Differentiate that implicitly with respect to time. Why time? Because I'm given stuff about dA dt, dr dt, so I differentiate with respect to time. Get this. And then when I look at this, I start looking at each of these pieces. dA dt I have, right? It's given, right here. dr dt is what I want, so I'm happy to see that. The only thing I don't have is the radius, do I? I don't have that. But now you can solve for r, because you've already done the derivative, right? So now you can freeze everything in time. So to figure out what this r is, what we're going to do is we're going to go back to here, and we're going to figure out what r is using this fact that the area is pi r squared, but I know the area is 5, right? I know the area is 5. And if I just divide both sides by pi, I get r squared. And then I can take the square root on both sides. And I only need to really consider the positive root because obviously my radius isn't negative, right? So that would be my r.
So I can plug that in here now. 1/5 equals pi times 2 times the radius, which is the square root of 5 over pi, times dr dt. And we're trying to solve for what? Dr dt. Okay, so we just got to get this by itself. So this was more scratch work on the side here. All right, how do we want to do that? Do we want an exact answer? Do we want a decimal answer? You want to do decimal? Yeah, let's just do decimal, I guess. Did you solve it already? You got something? I'm getting my calculator out. Let me, before I get my calculator, let me do something here. Can I erase this right here? All right. Okay, let me show you how I would solve that if I were doing that to do it exactly, right? So first thing I do is I divide both sides by 2 pi. And that would give me 1 over, what, 10 pi? Equals root 5 over pi times dr dt. So just divide both sides by 2, divide both sides by pi. And then to get rid of this, I divide by this or multiply by its reciprocal. So if I multiply by the reciprocal, I had to get root pi over 5 and then times the 1 over 10 pi. But remember, this 1 over 10 pi is not inside this root. And yeah, I mean, there's all sorts of different things you can do here. I'll just leave it like that. Just do this on your calculator. Do pi over 5, take the square root, then 1 over 10 pi. I'll tell you what I get. You got, what is it? 0.025? 0.025. I'll check. Approximately dr dt. And this will be measured in feet per second. Why feet per second? Because our radius is on top. R, right? Radius is measured in feet, and then time is measured in seconds. But let me just double check that. Not that I don't trust you, but. Yep, about 0.025231. So if you have a circle that's growing so that its surface area is increasing at a constant rate of 1/5 square feet per second, then at the exact moment that the area of that circle is 5 square feet, the radius is growing at 0.025 feet per second. All right, let's take a break. We say we come back in about, you don't want a full 9 minutes, or you don't want 5 minutes? What do you want? 8, 9, 10, 20? No, let's go till 2:50. So about 8 minutes. We'll take a break. And we'll come back and we'll do more word problems. Anybody have any questions on this? Yes? Oh, we're going to do a lot more problems. Yeah, don't worry. We're going to spend the rest of the time.
Can you explain the last part?
This right here?
Yeah.
So what I'm doing here is I'm looking at this as really being that. Like a root of a fraction, you can break it into 2 roots. And then to get rid of this fraction, I multiply by the reciprocal. So that flipped over. If I do that on this side, pi, root 5 like that. I do it on this side. They go away here, right? And then that's this. The 10 came from this step right here. I divided both sides by 2 pi. And when I divide by 2 pi, it shows up on the bottom over here. And that becomes 10 pi. Yeah, just ask. Don't hesitate to ask. Yes.
It was the same question.
The same question? Okay.
I think it was for facts. I was writing.
Okay.
Yeah, so I'm just scared.
Very good. Any other questions? Yes.
So, when something comes for the ride, is that just like simplified product rule?
Yes, you can look at it as a simplified product rule because anytime you would do a product rule when you have a constant attached, it would wind up being 0.
Okay, cool,
Yes? Okay.
cool, thanks.
Yep. So that's why if you have a constant, just do the come for the ride because if not, if you do the product rule, it's going to go away, right? When you
So
do.
it's the same as like, I was missing the point earlier about chain rule, where it's just, it's power rule is just simplified chain rule.
Yeah, you could, yeah, and then the
Comes for the ride is just simplified product rule.
yeah, you could look at it that way.
Okay.
Yep. But it really comes from the fact that when you do a derivative, the derivative is a limit. And whenever you have a limit, you can always pull constants out front. So that's really where it comes from. But it turns out that the product, if you try and do a product rule, like let's say you have 5x squared, you want to take derivative, then if you try a product rule, you're going to get the same result as bringing the 5 for the ride. So yeah, if you want to look at it as a simplified product, you can.
Okay,
Yeah.
thanks.